The basic notion on the semantical side is that of a structure. So a structure provides a domain over which we can interpret terms and formulas of a given language. So formally, it consists of the following parts. One is a non-empty set. That's called the domain or the universe of M, of the structure. So those will be the elements that we can interpret variables over, for example. Then, for every constant symbol in the language, we have to provide an interpretation of that constant symbol in our domain. So every constant symbol C will be assigned an element of the domain or universe, and we denote this by C to the M. Then, for every function symbol, we have to assign that a function, right? If the function symbol has arity n, we have to assign that a function f to the m that maps n tuples in M to M. So it's important that this function actually is a function from M to the n to M. Finally, for every relation symbol in our language, for every n-array relation symbol, we have to provide a set of n tuples in M. And we usually write L structures also as tuples, where the first part of the tuple is always the domain or universe, and then all the interpretations of the symbols in the signature of the language. So this will be much clearer from the examples how this notation actually works. So let's look at a few examples. Let's start with the language of rings. So 2 constant symbols and then 3 binary function symbols. And a structure over that language would be, for example, the integers with 0, 1. Right, so we interpret the constant symbol 0 as just the integer 0. The constant symbol 1 will be interpreted as the integer 1. And then plus, minus, and times are just the corresponding operations on integers. So there you see, like, you choose the language usually with the interpretation you have in mind for this. Right? A different example of that, of a ring structure over the language of rings, would be the complex field of complex numbers. Here now, those would be the complex number 0, the complex number 1, and this would be complex addition, subtraction, and complex multiplication. Let's look at a different language. So here we have a language where this here is a unary function symbol. And this here would be symbol would represent a binary function. And now we need to interpret this, right? So we have to first give, of course, our universe. Let's say this is R. And then we can interpret this unary function as the exponential function on R, right? And again here, the interpretation is as the notation suggests. And we would interpret this symbol here just as multiplication on R, right? Because we need to interpret it as a binary function symbol. But we could also do something very different and even counterintuitive. So if you look at this here, you would see at the next example, well, we could take the positive real numbers. And since this here is a unary function symbol, any function that is defined on all positive real numbers and maps positive real numbers to positive real numbers would be a valid interpretation. So we could actually make it the log function, right? So here, this looks a little bit weird, but it would be a valid structure, right? Of course, you would not do this in practice because it would be very confusing to interpret a symbol that you name x as log, for example, right? And you could interpret then this binary function as addition, which is fine. Let's look at a few more examples. So here we have a language of matrices, constant symbol, remember, unary function, and those two were binary function. And then, of course, a standard structure for that language would be, for example, the real value 2 by 2 matrices. We interpret the constant symbol as the 2 by 2 identity matrix. T would be actually then be interpreted as matrix transposition, right? The transpose. And those two symbols would be interpreted as matrix multiplication and addition. The final example, we take the language of sets. Remember, that was just the language that had just one binary relation symbol, right? So this here is a binary relation. And so what do we need to do? Well, we have to give a structure that has a universe that's non-empty. So why not take the set that just contains the empty set? That's not an empty set, right? It has one element, the empty set. And then we need to give interpretation of a relation symbol, right? But we just this can be any subset of the universe squared, right? So in this case, we can even choose it to be the empty set. A very different interpretation, but still valid, would be to take as the universe the rational numbers. And since this is a binary relation, any binary relation on the rational numbers would be a valid interpretation. So why not take just the less than relation on the rational numbers? That would be a valid structure for this language, but again, it's not a very intuitive interpretation, right? Usually, as I mentioned before, one chooses the symbol to actually set the context for the interpretation in the structures that you want to do. A fundamental relation between structures is that of isomorphism. So structures over the same language. And it generalizes or captures the basic idea that an isomorphism is just a structure preserving bijection between domains. And in our case, structure preserving means we have to preserve all the symbols that are present in the language, or rather the interpretations of these symbols. So here's the formal definition. Suppose we have two L structures, M and N. An isomorphism between M and M is a bijection from N to N, between the underlying universes, that is, such that the following holds. So the constant symbol, whenever I have a constant symbol in the language, the isomorphism pi has to map the interpretation of that constant symbol in the first structure, M, right, to the interpretation of that constant symbol in the second structure, N. For functions, right, that our isomorphism has to satisfy the following. Whenever I give you a tuple, so let's assume we have an n-array function, and I give you a tuple of n elements in M, right, then the value I get by applying the interpretation of the function symbol f in M to that tuple and then mapping it over to the n side is the same value that I would get by first mapping over these values of the AIs over to the n side and then applying the interpretation of the function symbol f there. So finally, for every relation symbol, so n-array relation symbol, and all elements a1 up to an from M, the relation holds for these AIs in M, right, in the interpretation of R in M, if and only if their images hold for the relation symbol interpretation of the relation symbol R in N. And as usual, we use this symbol here to denote isomorphism. Here are a few illustrations of this concept of isomorphism. So for example, for constant symbols, the condition is that if we have the interpretation of a constant symbol here in M, which is just an element of M, that element has to be mapped by pi to the interpretation of the same constant symbol in N. So for functions, we obtain the following picture. So let's assume we have a binary function. So a binary function will take two elements of the universe. Its interpretation in M will map this to another element in M, right? And the same thing happens on the N side. So the condition for an isomorphism is just that it doesn't matter whether I first map those two elements, A1 and A2, over here to pi A1 and pi A2, right? And then map them using the interpretation of F on the N side, or whether I first map them on the M side to using the interpretation of F and M, and then use pi to map them over here. In both cases, I land on the same result, right? I get this element here. Finally, for relation symbols, we have that, let's say we have a ternary relation here, interpreted in M. So whenever I have three elements for which this relation holds in M, then that happens if and only if the relation in N holds for their images. Here are three examples of isomorphic structures. Let's start with the structure, this language here. So this would be a constant symbol. And then we have a binary function. And the structures are, on the one side, we have the real numbers, interpret the constant as 0, and binary function is plus, right? The other structure is the positive real numbers. We interpret now the constant symbol here as 1, and the binary function is multiplication, right? And the isomorphism, of course, is given by the exponential function, right? Because what is the condition now for the isomorphism? Well, we would have to have that for the function, right? We'd have that a plus b, pi of a plus b, is equal to pi of a times, because that's the interpretation of the function here over on that other side, times pi of b. But that is, of course, given by the exponential function here, right? Because we know that exponential function of a plus b is exp of a times exp of b. And we also see that the condition for the constant symbol is satisfied because exp of 0 is 1. Next, let's look at the language of orders, right? Let's take the structures actually to be the same on both sides. So there, of course, the identity is always an isomorphism, but there can be isomorphisms, or in this case, of course, automorphisms that are not the identity. And in this case, we could look at just taking an element, an integer, and adding 5 to it. So for our condition, we would need, for example, that a less than b here holds if and only if pi of a less than pi of b holds, right? Which, of course, is the same here, would be a plus 5 less than b plus 5. And you see that this condition here is satisfied, right? This condition is satisfied for this mapping. For the final example, we look at this language here. This is called the language of groups. So this is a constant symbol, right? Of course, intended to represent the neutral element. And this here is a binary function symbol. And here on the structure side, what do we have? So these are just the unary sequences, unary strings, over the symbol 0, over 0, right? So the the universe would be would have elements something like this. Right? This here is the empty string. So this unique string of length 0. And this here would be concatenation. So just concatenating two strings is the binary operation. Okay. On the other side, we have the natural numbers. We have the 0 as the interpretation of the constant symbol and plus as the binary operation. And the isomorphism is provided by mapping a string, right, over zeros to its length. And you can see the empty string is mapped to 0, right? And we also see that if we concatenate two strings, one of length m and one of length n, then it's the length of that string, right, will be just m plus n, so satisfying the function condition for isomorphisms. Now that we have the notion of a structure, we can start evaluating terms and formulas or in those structures. So let L be a language and let M be an L structure. An M assignment is just a function that assigns every variable. So keep in mind here, recall that these are the variables of our language. They are always given to us, right? And we just map any variable to an element in our domain. So that assigns variables a value in the domain. And once we have that, we can evaluate terms by extending our assignment, alpha, inductively in the term height. So that then works as follows. So alpha bar here denotes the extension of an assignment alpha to all terms. Of course, every variable is a term, so we just use alpha as the basis for this. So if our term is just a variable, then we just use alpha. Similarly, if our term is just a constant symbol, then we already have a value for that constant symbol by the definition of a structure, right? Because the structure has to interpret that constant symbol. So there we just use that value, right, that interpretation of the constant symbol in the structure as our value for a bar. And then once we have the two base cases covered, we can now extend this inductively, right? If a term is of the form ft1tn, right? Then to extend it, we just use our a bar that's already defined for the smaller terms here, right? And apply the interpretation of the function symbol in m to it. This gives me again a value in m, right? At this point, it's probably good to fix some notation. So remember, alpha bar was our extension of an assignment alpha to all terms. So we will also write t, so the term interpreted in m, in the structure m, using the assignment alpha as our basis. Right. Then we can observe the following fact. So the evaluation of a term depends only on the values of the variables that occur in it. If m assignments alpha and beta agree on all variables that occur in T, then its extension to terms actually gives the same value on the term. This is of course not, it's not completely obvious. It needs to be proved. So as usual, I encourage you now to pause for a few minutes and think how you would do this. It clearly looks like you could use induction on term height here. So this observation then allows us to actually restrict our attention and our notation to a finite set of variables, because a term is a finite string, so at most finitely many variables can occur in it, right? And we use this notation to indicate that T is a term, and the distinct variables here include all variables that occur in T. So they include all variables. So they don't have to necessarily all occur in it, but the ones that do occur in T are among those variables here. And if T x1 xn is a term, and alpha of xi, right, assigns it the value a sub I, we use this notation T to the m square bracket a1 up to an for this notation. So for T to the m of alpha, right, square bracket alpha. And this is justified, right, because that value here, as we observed here, only depends on the assignment I actually do to the variables that occur in T, so in particular to the variables here, because they are among those xi's what I assign. So in particular, depends only on what I assign to the AI's here. So one last notational thing. Sometimes we want to change the assignment of a single variable given an assignment alpha. So that we denote as follows. So we denote this assignment alpha x to a. Just this denotes the assignment if x is equal to v, right, or v is equal to x rather, then we map this v to a and just carry over the rest of the assignment for all other variables. Now that we have values assigned to terms, we can now move to formulas. So we can use the interpretation of formulas and values in M to assign a truth value to a formula. Right? So the basic relation here will be that, in this notation here, and you can think of this notation as meaning phi is true in M under the assignment alpha. Or you can also, sometimes it's thought of as phi is satisfied in M by alpha. So similar to terms, the satisfaction relation for formulas in structures is defined inductively. This time, of course, in the height of a formula. So we have two base cases. The atomic formulas, one where we just have an equality between two terms, and that holds in M. Well, each term gets assigned a value, as we just saw, as we just defined, by an assignment inside a structure, right? So we denoted those by t to the m of square bracket alpha, right? And we say that this formula holds in M, or is true in M, under alpha if those two values coincide. Similarly, right, if we have a relation symbol and a relation of terms here, right, this holds in M, or is true in M, if and only if the evaluation of each of the terms, right, this gives me an element of M, this gives me an element of M, right, if that n tuple here, if that actually holds, if the interpretation of the relation symbol R in M holds for this tuple. So once we have the two base cases, we can then move on to the cases where we build up new formulas using the logical connectors, right? The negation symbol is pretty clear. So this holds if and only if the negated formula that we negate here does not hold in M, or is not satisfied there. Conjunctions hold if each of the parts hold. Right? And finally, the existential quantifier, right? So existential quantification of a formula psi holds or is true in M, holds if and only if there exists actually a witness that makes this existential quantifier true. So in formally, that means we can find an A in M such that if in our assignment we now evaluate x to A, right, that then that formula under this assignment becomes true in M. So this is just a formal way of expressing the intuitively clear idea that an existential formula is satisfied in a structure if and only if you can find a witness for that existential quantifier. Similar to the term notation that we introduced a few slides ago, we can make a similar observation with respect to what actually influences the truth value of a formula in a structure, and observe that it's only assignments to the free variables that actually that this truth value depends on. In particular, if two M assignments, alpha and beta, agree on the free variables, right? So the variables that occur non-bound in phi, right? Then the formula under the assignment alpha is true in M if and only if it's true in M under the assignment beta. Again, this is not completely obvious. It needs to be proved. And again, please pause for a few minutes and think about how you would prove this. And again, you would follow, of course, induction on the formula structure here. So having that observation, we can now follow the similar notational convention as we did for terms. So if the free variables of phi are among those variables, we can therefore use this bracket notation with these finitely many values from M here, right? So we're assuming that alpha of the xi's are evaluated to ai, and that then this this assignment makes phi true in M, right? And again, since there can of any formula is a finite object, there can be at most finitely many free variables, so we can always write it in this form once we have the set of free variables, or a finite set that contains all the free variables. Finally, if phi is a sentence, remember a sentence was just a formula that had no free variables, right? Then we can simply write, then we don't need to worry about any assignment at all, right? Because there are no free variables that could determine that could possibly change the truth value here. So then we simply write M satisfies phi, or phi holds in M, or phi is true in M. And we finish this lecture with a simple example. So let this be the language of groups. Remember, this was one constant symbol intended to represent the neutral element, and we have a binary function right here. And in that language now, of course, we can formulate the group axioms, right? The standard axioms about the neutral element, the associativity, and the existence of an inverse, right? And then, of course, note that these are all sentences, so there's no free occurrence of any variable here. So now we can just say the conjunction of these three formulas holds in a structure, in an LG structure, if and only if M is actually a group.